In this video, I'm going to show you how to think about the lift direction and the magnitude for this section and a section that is further towards the tip. First, what I'll do is I will go to a single view, and to overlay the pressure over this, pressure on the plane, I will just turn this on. And I'll make the pressure contours somewhat transparent. So I'll double click on pressure contours on plane, go to render and change transparency to say 0.6. And you can play with that setting and say apply. And I want to get rid of these contour lines. So I'll deselect that and say apply. So that gives you the velocity vectors overlaid over the pressure contour. So you can see both the velocity and pressure in the same view for that plane. What I'm going to do is also maybe get fewer vectors. So I can go to velocity vectors on plane. And for reduction factor, I will select 2, which will plot every other vector. So I get fewer vectors. And I'm going to look actually from the other side. So if I manipulate the view using the middle mouse button by holding down the middle mouse button, instead of looking in this direction, I will look along -x. And that just flips the view. And I will zoom in using the right mouse button by drawing a rectangle. Okay, so that gives me the view that I was looking for. And let's think about the direction of the lift on that particular section, and also the direction of the the various what causes the components that lead to the relative wind. And for that, I will go to my PowerPoint slide, which is essentially the view that I was just showing you. And what I will do, let's see, that's essentially the view that I was showing you. And what I've done here is I've just sketched in, I've taken a snapshot of that, say using the snipping tool. I can use the snipping tool, say in Windows, and take a snapshot. Or I can use this camera icon to save a picture. And then I made a PowerPoint slide out of that. So let's think about first the relative wind. That is the direction of the wind that's coming and hitting the blade. So that is going to be the wind direction. So this is away from the blade. Hope that's not confusing. And that's an input. And then that's the direction of the relative wind. So I got the direction of the relative wind from here. I just drew it a little bit longer than over here to see it. And you'll see in a moment why that is. So this is the relative wind. And this is where I need the velocity vectors away from the blade to see what the direction is. Which means that this component here has to be omega r, omega being the rotation rate, and r being the distance from the rotation axis. So r is -10 for this particular section. So you see how the contribution of omega r and the free stream lead to the relative wind. And omega r, because the blade in this view, if I was looking from the top, the blade is going to move in this direction. So if you're riding with the blade, it seems like there is a component in this direction, and that's like in this direction if you're riding on the blade, and that's omega r. Hope that's clear. So you see how that relative wind is constructed. And all I'm doing here is I've taken this arrow and drawn it here next to the chord, because that will shows me, oh, that's my angle of attack. And that depends on the design. For this particular design, that's the angle of attack at that section. And the lift force has to be perpendicular to the relative wind. That's the definition of the lift. It's perpendicular to the, the free stream, that is, as you're riding on the blade. And so let me call this DFL, L standing for lift, and DF because it's a small, this is the contribution of this section to the lift force. And I can decompose that into these two components, and I'll explain why I'm doing that. First, let's take a look at this component. That is in the direction of the wind, and so that's pushing the blade back, and that's kind of intuitive that, hey, I have wind hitting the blade, and that's going to push the blade back, and so I'm going to call that DFN for normal to the rotation plane. This is often called the thrust. That means this is going to be the component of the lift in the plane of rotation. So I'll call this tangential because it is tangential to the plane of rotation. This means that this is causing the blade to rotate. And you can see that, so the lift contributes to the thrust as well as the tangential force. And this is what we are really interested in, because that's what is causing the blade to rotate, and that contributes to the power. Now, what happens when you go further out, say at x equal to minus 25 instead of x equal to minus 10? And I can get that view by just going to plane and changing this to minus 25 and saying apply. So it'll update the plot for that plane, and here the velocity is much higher because it's further out. So I'll go and say make my symbols a little bit smaller. Okay, so here the velocity is around 75, and you'll see it's around 40 at x equal to minus 10, something like that. It's much lower. So I'll go back to this view. So that's, I've just taken this and put it on on my PowerPoint. And this is the relative wind vector we had for the previous section. Let's compare it to the relative wind for this section. For that, first I'll go to first I'll draw I'll sketch in. This is the same, the wind. This is same as for the previous section. And this is the relative wind. So this is parallel to these vectors. I've just drawn it longer because the wind velocity is higher at, where x is minus 25. And you can look at the level of the contours and confirm that. That means that has to be omega, let's say that's R2. So R2 is minus 25. Because R2 is greater than, the previous R for the previous section, this has to be much higher, which means that the relative wind is in this direction compared to this. So you see the relative wind as I'm going out, it's more it becomes more and more parallel to the plane of rotation, which is the XY plane here. That's because omega r becomes larger and larger. And in the limit, as omega r becomes very large, in fact, the relative wind will seem like it's coming from here. Okay. And so I've just reproduced this line as before over here just to see, what the angle of attack is. And that again depends on the design. And the lift force is perpendicular to the relative wind. And so that's DFL. I drew this much longer than the previous section. And you can you can confirm that the pressure differential between the lower surface over here and the upper surface, that's what is causing the lift, is much higher in the, when you go out. And to see that, so let's say I go to pressure contours on the plane, and let me say default legend view. Let me make this fixed. You'll see the effect of this in a moment. So, I just switched from scientific notation to fixed notation because my brain can read this a little bit more easily. So here the pressure differential between the high pressure here and the low pressure here is about, what is it? This is minus 2,000. This is about, let's say, 650. So it's about 2,500 or so pascals. And if I go back to the previous section, which was at minus 10, I believe, you see, and I have to double click on the pressure, it's about, let's say 600. So it's much higher. You see the pressure differential is much higher when you go out, which is why I drew this much longer. And if I again decompose it into components, in the normal and tangential, you see most of it is causing is contributing to the normal force because the lift has become, has rotated in this direction. So, and in the limit as rotation rate becomes very large, this is going to be actually perpendicular to the plane of rotation, and this is going to become negligible. Which is why, as beyond a certain rotation rate, you get a decrease in power, and that's why you have like an ideal tip speed ratio. And you have to spend some time with this, and you can see that while the lift becomes larger, its direction becomes less favorable because most of it is going to just push the blade back, and so there is a balance, and that's the ideal tip speed ratio gives you the right balance between those two factors. And the last thing I wanted to show you is saving the project. So if I say File, Save, in this case it says save a copy, and I can save it in the, I'd say yes, okay. And I can overwrite my WBPZ here because I started it from a WBPZ. The important point I want to make is that you can use file archive as shown under the save video earlier in the tutorial. You can create this WBPZ file, Z for zip, and I started it. I right clicked and said open with Workbench, and so that's why when I say file save, it's overwriting it. Otherwise, you have to do file archive and then create this WBPZ file. And you can see it should be a big file, and that has all your stuff. So you don't have to worry with the J file and the associated folders, which is mess. I hope that helps.